Logarithmic functions. So if you remember, every exponential function which has this form, a to power x, where the base a is a fixed number that's positive and different than 1, if you remember the graph of such a function, it depended on a, right? If a is a number between 0 and 1, there was a certain trend, and if it's bigger than 1, it was another trend, right? So let me remind you of this, of the graphs from the previous section, the exponential section. So when a is bigger than 1, we used to have this trend for ax, and when a is between 0 and 1, that's the blue trend is the graph, right? In both cases, we can see that the function is continuously monotonic in the sense that the left side is continuously increasing and the right side is continuously decreasing, correct? And as such a function, the pink and the blue, passes, or they both pass the horizontal line test, correct? They pass the horizontal line test, and from the section, the inverse function section, we know that this function is going to be 1 to 1, right? So this is the comment here. So such a function, a to power x, where a is positive and different than 1, is a 1 to 1 function by the horizontal line test. And then therefore we know from that section, the inverse function section, we know such a function has an inverse, correct? So the inverse function f inverse, remember this is the notation for inverse function, is referred to as the logarithmic function. So the inverse function of exponential function is referred to as the logarithmic function with base a, right? It's the same base. And the notation is like this, where this is a placeholder for the input, okay? So record the general property for inverse functions. F inverse assigns to a number y. So f inverse assigns to x a number y if and only if f assigns to y the number x, correct? So f inverse undoes the action of f, right? They undo each other, these two functions, a function and its inverse. So f inverse takes x to y if and only if f takes y back to x. Make sense? I mean, this is the property that we talked about back in the other section, the inverse function section. All right, so this leads us to the following definition of the logarithmic function. So let's see. Given a number that's positive and different than 1, the logarithmic function with base a, that base a, denoted by log base a, like this, is defined by, just read this part and rewrite f inverse by replace f inverse by the inverse function of the exponential function with base a. So this becomes log base a of x, right? This is this side, is equal to y if and only if the exponential function with base a acting at y. What's the exponential function with base a acting at y? It means a to power y, right? Is equal to x. Correct? So this is the property over here. That's exactly this, but this is for general function, an abstract function f. We're specializing f in this context to be what? To be the exponential function with base a. And as such, the inverse function is going to be referred to as the logarithmic function. It's going to be defined by this property, which in this case turns out to be this one. Correct? All right, so if you want to put it in words, you see the comment here in blue? Let's make sense of it. Look at this part. Log base a of x. If you call this guy y, this is what this is saying. If you call this guy y, what does y have to verify? Well, y is the guy that you place it as an exponent to the base a, in order to get an x, or to get not an x, to get the x. that x that sits here. Make sense? One more time. So if you call this image y, that's the same thing as saying that a to power y, and who's y? That's the log base a of x, right? So that means if you raise a to power y, which is the log base a of x, it should be x. Make sense? So you can say the following then. Log base a of x, the y guy, is the exponent to which a must be raised in order to obtain x. Right? So one more time. The y guy, which is log base a of x, right? The y guy is the log base a of x. That's the guy which I need to take the base a to that power in order for this entire exponential expression to turn into an x, right? So this sentence that you see in blue. Okay, so it's the exponent to which you should raise a in order to obtain x. All right. How do the graphs of log functions look like? Well, we used to have, log function with base a is the inverse function of the exponential function with base a, right? And what's the relationship between a function and its inverse? They are symmetric with respect to the line y equals x. If you remember back to that section, the inverse function section, we know that the inverse function and the function itself are their graphs are symmetric with respect to the line y equals x. Since log base a of x is the inverse function of the exponential function with base a, that's going to be symmetric. The graph of log base a is going to be symmetric to the graph of the exponential function with base a with respect to the line y equals x. Okay. Well, we used to have two trends for the exponential function with base a, the pink and the blue. So I'm going to have two graphs for the log function with base a, depending on what a is. If a is bigger than 1, so the symmetry of this with respect to the line y equals x is going to be this pink thing, right? Remember, y equals x is the only line, is the only axis in the plane that allows you to swap coordinates, correct? So the symmetry of 0, 1 with respect to the line y equals x is going to be the point 1, 0. It's going to swap the coordinates, correct? So you get this. So that point is the symmetry of 0, 1, and so on and so forth. So you do it point by point, and you're going to get exactly what you see on the other screen. So, for example, here, look, this x is large negative here, right? Like negative a million or something. And the y coordinate is so small. When you reflect this in the line y equals x, you're going to get the x so small, but the y is large negative. And that's reflected over here, right? So the x is so small, and the y is so small positive, and the y is large negative, correct? So this is the symmetry of the line, of the curve ax, where a is bigger than 1. And when a is between 0 and 1, the trend is like this for exponential function with base a. So the log function with base a is going to be this one, right? Also is going to intersect the x-axis at 1, 0, because the exponential function used to cross the y-axis at 0, 1. Make sense? All right. And what used to be the domain of the exponential function, remember the domain of a function is the same as the range of its inverse, right? So, and vice versa. The range of a function is the domain of its inverse. They go back, where a function picks up is where the inverse function is gonna land in some sense, right? So what I'm saying is the following: if f goes from a set A, the domain, to its range, let's call it B. Let's say B is the range of f. Then f inverse is going to come backwards, right? We talked about this back in that section. So the domain of f is going to be the range of f inverse. And the range of f is going to be the domain of f inverse, right? So where f inverse starts is where f finishes in some sense, or where f lands. Okay. All right. So so as such, since the function, the exponential function with base a, has domain r, the range of the log, the range of the inverse function of this, which is the log function with base a, is gonna have range r, or real numbers. And since this guy has range 0 plus infinity, the inverse, which is log base a, is gonna have domain 0 plus infinity. Okay, so this is what I have here. Makes sense? So the log of the function, the log function with base a, has its domain what used to be the range of the exponential function with base a, and log base a has its range what used to be the exponential, the domain of the exponential function with range a. Makes sense? All right, and as x goes to minus infinity, I mean, here we had y equals 0, which is the x-axis, a horizontal asymptote. Now this is going to turn into, remember the symmetry of y equals 0 with respect to the line y equals x, is going to turn it into x equals 0. So now you're going to get the line x equals 0, which is the vertical axis, the y-axis, is going to be a vertical asymptote, meaning the distance between the graph and the line eventually decreases to 0, right? So they're gonna hug each other when the input is slightly bigger than 0. Make sense? All right. So the domain log base a only operates on positive number, right? Log base a only operates on positive numbers. All right, very good. And it outputs things in R, right? Look at the nature of the graphs. The graphs of log base a, and in both cases, it's all real numbers, right? It's all real numbers. Okay, very good. Okay, let me now ask you to do the following. Let's take a function. So a little exercise. Let's take f to be a to power x, the exponential function with base a, and g of x to be log base a acting at x, right? So these two functions are inverses, by definition, right? So let me just erase this and rephrase it as follows. So let f be this, then it follows that f inverse of x is going to be this much, right? Okay. Oops. So what can we say? Then what I want to ask you is, I want you to compose the two. We know that f composed with f inverse acting at x is x, and this is for any x, and this is for any x in the domain of f inverse, right? Because x here is going to f inverse. And what's the domain of f inverse? The log base a function. It's 0 plus infinity, right? We just talked about it above. And what do we also know? We know that f inverse composed with f acting at x is equal to x, and this is for all x now in the domain of the function f, because x is going to f now, and the domain of f, which is the exponential function with base a, is already numbered, right? All right. How about we unravel what this side means? in this context. How about because these two properties hold for all for any function f and its inverse, right? In this case, what does this mean? What does this right-hand side mean and this right-hand side? What do they mean? How about we give them names? Let's call them asterisk and double asterisks. Okay. So then the right-hand side of the asterisk, so thus the left-hand side of asterisk is f composed with f inverse of x, which is equal to f of f inverse of x, right? And what's f inverse of x? I'm going to replace what f inverse means, right? F inverse of x means. Well, f inverse of x means log base a of x. It's on the screen. Log base a of x. And what does this last expression mean? F of this guy, well, f of anything is a to the power that thing, right? I repeat, f of anything is equal to a raised to the power of that thing. So who's the thing here? Who's the guy sitting here as who's the guy replacing x in this equation? Well, it's the log base a of x who's replacing x, right? So one more time, f of something is a to that to power that thing. My thing here is log base a of x, so that's going to be a to the power log base a of x, right? So this is what's going to happen here. That's equal to log a to power log base a of x, right? So we can fix this. A to power log base a of x. So asterisk, the left-hand side of the asterisk equation or identity can be, or is the same as a to power log base a of x. That's this guy, correct? So asterisk is equivalent to as we said, the right hand side is the same as a log base a of x, so is equivalent to a log base a of x is equal to 2x, right? 2x. And this is, as we said above, for all x in 0 plus infinity. Okay, so I'm gonna highlight this for you. So this is a property that we can use at any moment. We just proved it. Okay, I mean this this is exactly what we had before, right? I mean, in the definition of log, right? Just replace y by log base a of x. You put it here, you get exactly what you see over here, right? I just wanted to come to it also from this way to just to show you how things are intertwined. For double asterisk, let's do the same thing for the right hand side of the double asterisk. So also the left hand side of double asterisks is it's f inverse composed with f this time, right, at x. And now x can be any real number. Well, this is the same as f inverse acting at f of x. This is how you compose two functions, right? All right, so f inverse is going to operate on the output of f when the input is x. Well, what is that? What is this guy, f of x? Well, f of x is a to power x. So that's going to be equal to f inverse of a of x, right? Why? Because f of x f of x is ax, a to power x. So you get this. And now f inverse, how does f inverse operate? Well, f inverse acting on something is equal to log base a of that thing. Whatever the input here, it's gonna sit right there, right? It's the log base a function. This is what f inverse is. So f inverse of that is gonna be log base a acting at ax, right? Right, so f inverse is the log base a function. It's gonna act on this, so it's gonna be written as such. Make sense? So now double asterisk, how can you read double asterisk at this point? The left-hand side, which we just unraveled what it means in our context, it means this expression. So this expression replacing this is equal to x for all x in R. So I'm gonna record this. So double asterisks is equivalent to the left-hand side of double asterisk, as we said, is this expression, which we just realized what it means. In our context, it means this piece. So it means log base a of a to power x is equal to x. And as we said above, this happens for all real numbers, right? This happens for all real numbers. You see this? That's exactly what I have. Let me also highlight this for you as I did for the other one. Okay. All right. So these are the two properties I'm gonna be recording on the next page. I want you to think about these as follows. I mean, look at the nature of both highlighted equations here, or properties. Because f and f inverse undo each other, they neutralize each other's effect. When you see the exponential function with base a back to back with log base a, in any order, right? In any order, whether the log operates before the exponential function or the exponential function operating before the log base a, they undo each other, and the remaining thing is, I mean, the answer is whatever is sitting here, right? They undo each other, so they neutralize each other effect, as they should, because this is their definition. This is how they are defined. Okay. All right. So so this is the next properties. You see properties 3 and 4. They are these highlighted ones. So these technically, this discussion that we had here in this exercise, this is the proof of the properties that you see in 3 and 4. Make sense? Okay. In addition, I'm gonna also write two other properties, 1 and 2, but they are part of property 3. Look, when property 3 property 3 holds for any real number x, right? For any real number x. So no matter what x you choose, this is always gonna be true. If you choose x to be 1, well, this is gonna be log base a of a to power 1, right? And what's a to power 1? It's a, right? So you're gonna get this side is equal to that guy 1, right? So property 2 is part of is implied by property 3. So property 2 is not something that's not known if you just have 3 by itself, right? Okay, it's a specialized property, or it's a specialized case of property 3, namely when x is 1. Okay, now if x is 0, if you replace x by 0 in property 3, which you're allowed to do so because x can be any real number in property 3, if you replace x by 0, so you get 0 here, 0 here, right? And what's a to power 0? What do you know about a all along in this context? A is a number that's positive and different than 1, right? So if a is a number that's not 0, raise it to power 0, that's a 1 here. That guy is 1, so you get this left-hand side of property 1, and this side is 0. So log base a of 1 is equal to 0. Make sense? Okay, so property 1 also is part of property 3 for a specialized x. And this is part of the picture. Let's try to go to the picture. This tells us that on the graph of log base a, function, when the input is 1, the output is 0. So 1 comma 0 is going to be part of the graph of log base a function. Well, we know this. When the input is 1, the output is 0, right? When the input is 1, the output is 0. So it's just telling us, it's just talking about such a point, right? All right. Okay, let's go to the book. This is section 3.3, page, let's start on page 392. Let's do, let's start, let's say, by number 10. Okay, so what's the question here? The question is, write the equation in exponential form. Okay, so I want you to read these two questions for problems 9 through 16 and for problems 17 through 24. This question is, write the equation in exponential form, and this one is, write the equation in logarithmic form. Let me just tell you what these questions mean. You see this side? Remember the definition of logarithmic function with base a? This side is referred to as the logarithmic form, and this equation is referred to as an equation in exponential form. Okay, so logarithmic form, exponential form. Okay, because of, the nature of the equation, obviously. Okay, so let's just do one of them. So let's say number 10. We want to write this equation, which is in logarithmic form. We want to write it in exponential form, right? So log base 9 of 81. So this is on page, let's zoom in a little bit. Okay, this is on page 392. And we said this is number 10, right? Actually, let me erase this. Let's do this. All right, so we have log base 9 of 81 equals to, as we said, this is in logarithmic form. And if you go back to the definition, so I have here log base 9 of 81 equals 2. So I'm gonna write here. So who's the base? The base is 9, right? 9 to this power, which is 2 in my case, is equal to 81. Okay? So log base 9 of 81 equals 2. So a is 9, x is 81, and y is 2. That's the same thing as saying the equivalent equation in exponential form is 9 to power 2 is equal to that argument x, which is 81, right, in our context. Okay, so this is just to let you pass from one form to the next. This is equivalent to 9 to power 2 is equal to 81. Okay, all right, so nothing special here. Let's do one of these 17 through 24. They are they are written in exponential form, and they want to write it in logarithmic form. Let's just choose one of them. How about 20? 1 over 2 to power negative 5 is equal to 32. So 20. I have 1 over 2 to power negative 5 is equal to 32, right? Let me instead of going back and forth between here and the previous page, let me write it here. So the definition was log base a of x equals y. By definition, this is exactly the same as a to power y is equal to x, right? Okay, so we are here now, and this equation is given in this form, which is exponential form. We want to write it as this. So a is half, y is -5, and x is 32, right? So we want to use the definition again, where a is half, y is -5, and x is 32. And what do we get? We get log base the a, which is half, as we said, of x. And what's x? 32 is equal to the y, and the y is -5, right? Correct? So remember what this is, log base a of x, Remember we verbalized this definition, right? We verbalized it in blue here. Log base a of x is the exponent to which you should raise the base to get the argument, right? The x. So here, log base 9 of 81, this is the exponent to which you should raise 9 to obtain the argument 981, right? So to what power 9 is raised to get 81 is 2, so this guy is 2, right? And since it's a one-to-one function, you will not get more than, if you find 1, that's the only one, right? So that's why it's a uniquely determined thing, because the exponential function is unique, is one-to-one. So okay, so whatever this guy, once you find a guy, that's the guy. There's no more than this. All right, so also this means you should raise half to power -5 in order to get 32, right? Raise half to power -5, which means you raise 2 to power 5, and if you raise 2 to power 5, you get 32. Okay. All right, so let's keep going. Let's go to this group, 25 through 50. The question is to simplify the expression without using a calculator. You want to find the exact number. How about 32? So log base 3 of 1/9. So 32. Remember, we want to find the exact value without using a calculator. So we have log base 3 of 1/9, right? So what is this? That's the guy, that number, this whole image, is the number to which you should raise 3 to obtain 1/9. If you don't see it immediately, let's do it. So that if you call this y, what this means, based on the definition, is that you should raise 3 to this number in order to get 1/9. Am I correct? So this is the definition. It's right there. This is the definition. So a is 3, x is 1/9, and y is the thing I called it, right? So that becomes a to power y. So 3 to power y is equal to x, is equal to 1/9. Okay, so the question becomes, what's the power I should raise 3 in order to obtain 1/9? Well, 1/9 is 3 to power -2, right? 1/9 is 3 to power -2. Okay, maybe let me do an intermediate step if you don't see it. 9 is 3 squared, right? And this, by definition, this is 3 to power -2, correct? And now look, 3 to power y is equal to 3 to power -2, and the exponential function is a one-to-one function. The exponential function with base 3 is a one-to-one function. So a to power y is equal to a to power -2. Since the exponential function with base a is 1-to-1, the y must be -2, right? The y must be -2. So you get this. Makes sense? Let me show you a different approach. Let me do it in a slightly different way. So alternatively, we had log base 3 of 1 over 9. This is what we wanted to see, right? We wanted to evaluate. Well, that's the same as, you're gonna see the steps I'm gonna be making here are pretty much the same as we did over here. That's the same as log base 3 of 1 over 9, but 1 over 9, we just discussed it. This is 3 to the power negative 2, correct? And now look, this is of the form log base a of ax. Log base a of ax. What is it? It's part 3. Log base a of ax. They undo each other. It's the same. It's the logarithmic with a base that's the same as the exponential function with that base, right? So back to back, they undo each other. You get just that x. And x can be any real number, so you get just the x, right? So who's the x? That's negative 3. Negative 2. So this is negative 2. And let's highlight y. This is by property 3 and the properties we listed above, right? It was 3, right? Yes, this one. Okay. So we use property 3 with a is 3 and x is negative 2. Oh, I mean negative 2 here. I don't know why I wrote negative 3. I meant negative 2, right? Okay, so negative 2. Makes sense? So we use property 3 where a is 3 and x is negative 2. Okay. So we get this, which is exactly as we found in the other approach. Okay. So please feel free to use your own taste. Okay. Express yourself in that solution. Okay. Let's move on. Let's go also to the book. So we did 32. Let's do something here. How about 48? Log base 2 of third root of 2. Okay. Maybe this is easy. Okay, I'll do it. Let me do something that happened before. How about 46? 46 and 42 are pretty much the same almost. Let me do 46. Log base 3 halves. The base 3 halves is certainly different than 1 and positive, right? So this is a meaningful thing of 9 over 4. So this is 46 log base 3 halves of 9 over 4, right? I'm gonna do it as the second approach. You can still do it. I showed you those two things, those two approaches. I'm gonna do it this way. So log base 3 halves of, do you agree with me that 9 is 3 squared and 4 is 2 squared? So this quotient is the square of 3 halves. Do you agree with me? So 3 over 4 over 2 squared is 9 over 4. So this whole thing is the same as this whole thing, right? Okay. And now back to property 3. Log base a of ax. Back to property 3. Let me take you back there. Property 3. Log base a of ax for any real number x. That's x. So what's this guy then? That's the x. That's 2. So this is 2 by property 3 again, right? Okay. All right. Let's do the other one that I promised you that I want to do. Which one was it? 48. Log base 2 of third root of 2. Okay. Hope you now see the answer before you do it. 48 log base 2 of third root of 2. Okay. Let's keep doing the same way as we did in the green part. So log base 2, the third root of something is denoted by, notationally, this is the same as 2 to the power 1/3, right? The third root of something is that thing raised to the power 1/3. And then back to property 3, log base a of ax, log base a of the same ax, that's the x, right? Again, property 3, one more time. Makes sense. Okay. All right. Let's go to the next page. We can do these quickly. Look, how about 56? Let's do this quickly. Log base 6 to the power 7. I mean, log base ax. This is x again, right? By property 3, we just talked about it. This is how much? This is 7, right? This is 7. 57. Log base c of c. Log base a of a to power 1. So this is 1. It has also a property for it, right? Remember property 2. Log base a of a when x is 1 and property 3. This is 1. Correct? So log base c of c is 1. This is problem 57, correct? And likewise for 58. 57 and 58 are both 1. How about 59 or 60? How about 60? 4 to power log base 4 of a minus c, right? You see 60? Let me write it for you here. So 60, this is 4 to power log base 4, same base, a minus c, correct? Well, this is property 4 this time. I have exponential function with base a back to back with the logarithmic function with the same base back to back. They undo each other, and the answer is just that x, right? Because these guys can cancel or reverses each other's effect. Same thing here. 4, that's the exponential function with that base 4. Followed by, or actually the log is followed by exponential. So the log of the same base 4 back to back, neutral action, result a minus c, right? So a minus c is playing the role of x in property 4. Agree with me? All right. (64) log base pi of 1. Okay, they're trying to be like fancy here. Log base pi of 1. So what is it? This is 64, we said. Log base pi of 1. Well, log base pi of 1, we derived this result at the time, if you remember. We discovered this property 1. And the base a in this context is pi. Pi is certainly a number that's positive and different than 1, right? So log base pi of 1 is 0, right? Because this is the power to which I should raise pi to get 1. Well, raise it to power 0 and you got it. Okay? All right. So these are not bad at this point. Okay, so and from 71 to 78, you have to graph those functions. If you remember the previous section, the exponential function, here you're gonna start from a parent function which is log, but it's the same approach. So okay, you know what? I'll do one. I wasn't planning to, but let me do one because it's like a repetition here. Okay, so 76. We wanna use, let's use 76. We wanna use transformations of the graph. Which parent function for 76? It's log base 2, right? So we wanna start from log base 2. Do we know how to graph log base 2? Well, the base is 2, so it's bigger than 1, and we used to have 2 trans for this. The base is bigger than 1, so it's gonna go like this, right? It's gonna go like this. So such a function is negative between 0 and 1, and it's positive after 1, right? So we know how to graph log base 2. So the idea here is to graph log base 2 of x minus 2 minus 1, right? And we want to, for part B, want to find the domain range, and part C, write the equation of the asymptote. We're going to have, in this context, obviously a vertical asymptote, right? Because log is involved, and log has vertical asymptote, as we discussed in the lecture. Okay, so this is, we said 76. So our function y is equal, how about we give it a name? How about we call it f of x, and it's log base 2 of x minus 2 minus 1, right? Okay. So the parent function that I'm going to start with is log base 2 of x, and log base 2, since you don't have to put the parentheses here, since the base is bigger than 1, the graph is going to look like this. Okay, the graph is going to look like this, right? So this is log base 2 of x, which is the parent function p. Okay, let me write just p. Okay, and this point is what? This is 1 comma 0. Correct? And what's the asymptote? Let's keep track of this like we used to do in the previous section. The asymptote is the line, the vertical line, which is what? Which is x equals 0. Okay, so this is the vertical asymptote for the parent function p. Okay, so what's the idea again? The idea is to cook up the function f. And I have log base 2 of x. How about we inject this minus 2 as an intermediate step? Let's call this function omega of x. So what's omega of x? Omega of x is log base 2 of x minus 2. Okay? Log base 2 of x minus 2. This term. Let's find the algebraic connection between omega and p. Well, what does p do? P of anything is log base 2 of that thing. So what do I have? What's the situation I have here? Log base 2 of x minus 2. Well, the thing apparently is x minus 2 here, as the thing that we referred to here is x minus 2. So who's taken the role of this guy? X minus 2. So, and that guy is this guy, so this is p of x minus 2, right? Check it again backwards. P of x minus 2, p of x minus 2. So x minus 2 is taking the role of x. It's going to be log base 2 of that x minus 2. Okay, so this is the algebraic connection between p and omega. And if you know how to graph the graph of p, how do you graph the graph of p of x minus 2? This is a horizontal shift, right? This is a horizontal shift because you're shifting the input. And here you are delaying by 2, right? So omega is going to be slower than p by 2 units. Okay, so you're going to do a shift to the right by 2. Okay, and you're going to get so omega, as you said, is a shift of p by 2 units to the right. So everything is going to shift, the asymptote as well, right? Because those guys are getting closer and closer to this asymptote here. The whole thing is going to shift by 2. This new asymptote is going to be x equals 2. Am I correct? Okay. And then the omega function is going to be very much like this. That's omega, right? And what's this point? So what used to be 1, there's a delay of 2 now. I mean, 2 units to the right. It's going to be a 3 now, right? And finally, to find f, the graph of f, I'm still missing -1, right? Remember, this whole term is what we refer to as omega here, omega of x. So omega of x minus 1 is going to be f of x, right? So f of x is omega of x minus 1, okay? And how do you graph omega of x minus 1 if you know how to graph omega of x? You just shift the graph of omega by 1 downward, right? So you're chipping away 1 unit from the value, the output of omega. So it's a vertical shift. It's a vertical shift. You're shifting downward by 1. So we're going to shift the whole thing by 1. And shifting that vertical line by 1 downward, it's going to remain itself, right? So it's not going to affect the vertical axis, the vertical asymptote. So and then I'll get this. Actually, let me do it here. Okay, so that vertical asymptote remains itself because it's a vertical shift, so nothing happens to a vertical axis. And the graph is going to look like this, right? This is the function f. Okay, the question is, what's the intersect here? This is not anymore 3, right? This is not anymore 3. Because that point, if you want to keep track of this point, how about we call it the green point. You see this point? It's right there now, right? It's right there. It's at 3, -1, right? It used to be 3, 0. It's 3, -1 now. So what's the y-intercept? Sorry, what's the x-intercept? Well, if you don't see what the x-intercept, it's we gotta do it algebraically. Okay, we gotta do it algebraically if you don't see it. So let's find this point. So let us find the x-intercept of f. So to find the x-intercept, we want to find a number a such that f of a is equal to 0, right? So that point here has 2 coordinates, a, f of a, and certainly the second one is 0. We know that because it belongs to the x-axis, right? Okay. Well, f of a is equal to 0. Okay, I'm exhausting my limit here. F of a equals 0 means log. So f of a equals 0 means what's f of a? It's log base 2 of a minus 2 minus 1, right? This is f of x. F of a is going to be log base 2 of a minus 2 minus 1. So that's going to be log base 2 of a minus 2 minus 1 is equal to 0, correct? And this is the same as log base 2 of a minus 2 is equal to 1, right? I just added 1 to both sides. This disappears from here, it shows up here, right? And then log base 2 of a minus 2 is equal to 1. This means what? Remember this is an equation in logarithmic form, right? This is an equation in logarithmic form. Where did we do this? Right there. So remember these earlier problems? We have this form. We want to transition to an exponential function, an exponential expression, exponential form, an equation in exponential form. Why? Because what I want is I want to free the a, right? I want to free the a, and log base 2 is acting on a. So I want to undo the action of log base 2. So apply the exponential function with base 2 or transition to the exponential form. So rewrite this in exponential form. We get what? Remember, we get 2 to power 1 is equal to a minus 2, right? Correct. So what did we do here? A to power. Okay, what did I do here? Yeah, 2 to power 1, right? So what did we do in this step? Not this step. This step, we used, we passed to exponential form, right? So we rewrote the equation in exponential form. That's what we did. Why? Because I want to free the a. I don't want, I mean, like we used to do when we solve for a certain variable in an equation, we undo all the actions that are done on x, right? I'm undoing the action of log base 2 that's done on this expression which involves my a, because what I want to find is a. So let's free the a. Let's free the a, and freeing the a means I want to somehow cancel the log base 2, and canceling log base 2 means applying exponential function with base 2. What's the thing that undoes the action of log base 2? It's the function, it's the exponential function with the same base, right? Which means, or equivalently, you can say, okay, let's transition to the exponential form, to that equation, but in exponential form. You get this way. And then this means what? This means a is how much? Let me go back to blue. So this means a is how much? If a minus 2 is 2, right? 2 to power 1 is 2. This means a is 4, right? So at the end of the day, what's that number? This number is 4. Correct? Let me just write it here. Makes sense? Okay. Let's move on. Next definition. So the logarithmic function with base 10, it's called the common logarithm, as denoted by omitting the base. So log base 10, the notation is just log. Like we used for square root of 2, typically the index is, I mean, we should write the index, but for 2 we omit it, right? Something like this I'm talking about here in this definition for logs though. So if you see nobody on the leg of g, this means 10 is there, right? So we just drop it, and it's referred to as the common logarithmic function. Okay, but still, I mean, the same thing. The input in log base 10, the common log, is gonna be positive, right? As it used to be in for any logarithmic function before. And the last one, this definition here, very similar but a different base. The base is e. Remember e, Euler's number, introduced in the previous section. The logarithm with base e, logarithmic function with base e, is called the natural logarithm, as denoted by ln. So what's ln? It's a natural logarithm, but it's log base e, right? So it's a notation. ln is simply a notation for log base e, right? So people don't write this, they just represent it by ln. Okay, so nothing so special, it's just a notation here. Log base 10 is written as log, you don't write the base, and log base e, you call it ln for natural log. All right, so this is the definition, or the definitions. Let's now go to back to the book. You see 62? ln of e x2 plus 1. Remember what ln is? Is log base e, right? So the question here is simplify the expression. Let's do it. So 62. So 62. ln of, we want to rewrite this as, without the use of a calculator, we want to simplify it. ln of e to power x 2 plus 1, right? Well, ln is log base e. So that's the same thing as log base e of e to power this guy. So x2 plus 1 is the exponent. So log base a of a, that's the same, that this is back to back. Log base something acting on the exponential function with the same base. So they undo each other by property, I think 4 that we labeled above, right? I'm talking about this property, actually 3, right? So property 3, log base e of ex, and log base e, the notation is ln. So ln of ex is x. Whatever this x is, it happens to be x2 plus 1 here, right? So it happens to be x2 plus 1 here. So that's the same as x2 plus 1. I'm gonna just mention here that this is by property 3 in concert with the fact that log base e is written as ln. So log base a x2 plus 1 is x2 plus 1, right? Okay. All right. Those previous problems are very much the same. Let's do one of them. Let's go for 50. Log without any base means a common log. So log base 10, square root of 1 over 1,000. So this is number 50. So 50, I have log base 10, so the common log, square root of 1 over 1,000. Right? All right, like we used to do above, this is log base 10 of 1 over 1,000 raised to power half, because this umbrella, the index is 2, right? This umbrella means to power half. And this is equal to log base 10 of well, 1 over 1,000 is 1 over 10 cubed, right? 1 over 10 cubed. Agree with me? And 1 over 10 cubed is 10 to power negative 3. Yes? So 1 over the reciprocal of 10 cubed is 10 to power negative 3, right? This minus in the exponent means the reciprocal. All right. And now you use one of the properties for exponents. 10 to power negative 3 to power negative 2 is 10 to power negative 3 times half, and negative 3 times half is negative 3 halves, right? One more time. What do you do here? You're taking an exponential expression to a certain power, you keep the base and you multiply the powers. Minus 3 times half is minus 3 halves. Okay. And log without anything here means log base 10, right? Log base 10 of 10 to power minus 3 halves. So do you believe me if I write that this is minus 3 over 2 by property 3? By property 3 that we've been talking about all along so far, right? Log base a of ax is x, property 3. Go back and see it, please. Log base a of ax is x, right? And the x happens to be minus 3 over 2 over here. Excellent. Okay, so the last type of problems I'm interested in this section is this type. Write the domain and interval notation of those functions. Let's let me choose one. How about 86? Okay, how about 86? G of x is log base 7 of x2 minus 49, and I want to write the domain, right? So 86. Find the domain of the function. So find the domain of the function, which is given by g of x is equal to log base 7 of x2 minus 49, right? Okay, so what do we know about log base a, the function log base a? What do we know about this? Well, where is it? It's right there. Log base a has domain 0 plus infinity. What does it mean? It means that whoever is gonna be sitting here has to be positive, right? Make sense? So whoever sits here, whoever log base a is acting on, it should be positive because it doesn't accept numbers that are non-positive, right? It only accepts positive numbers based on the discussion we just had. Make sense? So log base a of x exists or is meaningful or makes sense whenever that x is positive, right? Okay. So back here, who's that guy that's sitting, that log base a, which is 7 in this case, log base 7 is acting on? That guy. That's the guy that log base 7 is acting on. So log base 7 of this guy is meaningful as long as this guy is positive, right? So let's zoom in. So g of x is meaningful, which means a real number, right? If and only if the guy x2 minus 49, who's the input in this log base 7 machine, is positive, right? Okay, so I want to see where this second degree polynomial is positive. I hope this rings a bell. One of the earlier sections, namely when we were trying to see where a certain polynomial is has a certain sign, right? Positive, negative, and so on. So I'm gonna treat it the same way. I'm gonna factor this polynomial. I'm gonna factor it, and then I'm gonna look at the product when the product is positive. If you factor this, it's not hard to see that this is a difference of 2 squares, right? X squared minus 7 squared. So this is x minus 7 times x plus 7. I want this product to be positive. Let's create a table of variations, right? Remember that? Table of variations. Let's create that. So I have x minus 7 as one of the factors, x plus 7 as the other, and then I have this product, right? Let's give it a name. Let's call this product, as we used to do before, P. So P is the product. All right, what are the critical numbers for the factors? Where does this vanish? It vanishes when x is 7, and this one vanishes when x is negative 7. So negative 7 and 7 are the critical numbers in this discussion. Okay. This is where x lives, right? Okay. All right. Then, as we said, this vanishes here. Before that, it's gonna preserve one sign, and that sign, if you test it, just take a number less than 7. Let's say 0, 0 minus 7 is negative, so the whole thing is negative here. And if you test a number bigger than 7, it's gonna produce a positive entity. For x plus 7, it's 0 at negative 7. Before that is negative, as you can check, positive afterwards. And then I can deduce information about the variations of the product. Well, the product is positive here, 0 at negative 7. Why? Because one of the factors is 0. Negative here, 0 at 7, again because one of the factors is 0, namely x minus 7. And after that, Both of the factors are positive, so the product is positive. All right. This is the information on P that I want. And the question is, when is P positive? Well, P is positive when x is between minus infinity all the way to -7, excluding -7, because at -7 P is 0. And from 7, I mean, any number bigger than 7, right? So then at the end of the day, what do we get? So this is like all this discussion that you see here, all this discussion is like needed to come up with this equivalence, right? The equivalence is that, the equivalence of what? The equivalence of the statement, right? The equivalence of the statement. And that's the reasoning here. That thing is equivalent to say that x is between or less than -7, or x should be greater than 7. Am I correct? This is what this says. X should be between minus infinity -7, excluding -7, because at -7 the product is 0, and you don't want the product to be 0. And similarly here, the product is positive for any x bigger than 7. Make sense? So long story short, g of x is meaningful if and only if x is either less than -7 or x is bigger than 7. So what are the good x that I can plug in G? They are numbers that are less than -7 or bigger than 7. So what's the domain? The question is, what's the domain? So therefore, the domain of G is equal to minus infinity to -7 union 7 to plus infinity, right? Okay. All right, let's do one more. Let's do 92, last one. Okay, 92. You have s of x as log base 5 of 3 minus x squared. So 92. So we have s of x is equal to log base 5 of 3 minus x squared. Okay. Same thing. S of x is log base 5 of this guy. So who's the guy that log base 5 is acting on? This is the guy. That's the guy that's going inside the machine log base 5. And log base 5 accepts positive inputs, right? So this whole thing must be positive then, so that s of x to be meaningful, right? Remember, log base a only accepts positive number because the domain of log base a is only is the set consisting of positive numbers. So that's the guy that's going inside the log base 5 function. As such, so log base 5 or s of x is meaningful or makes sense or exists, which means a real number. It's a real number if and only if the guy who's going in the log base 5 machine is positive. So as long as this is positive, right? Correct? Well, this guy is greater than or equal to 0 for all x. Agree with that? This guy, as it happens, this is greater than or equal to 0 because it's the square of a real number. No matter what x is, 3 minus x is a real number, right? So no matter what the real number x is, 3 minus x is a real number. Square a real number, you get a non-negative entity. Correct? So this is bigger than or equal to 0 for all x in R. For all real numbers x. So since this guy is at least 0 all the time, what do you want? You want it to be positive. So what do you need to exclude? So you want to exclude when it's 0, right? So you want to exclude when it's 0. Makes sense? So this is happening exactly when 3 minus x squared is not 0. One more time, let me explain this again. This entity here is at least 0 for all x. And what's your demand for s of x to exist? Your demand is that this guy is simply positive. So this is equivalent to saying that you want this not to be 0, because if it's not 0, then certainly it's positive, right? All right. So just ask for this and you get that. These are equivalent demands. Okay, so and the square of something is not 0 if and only if the thing is not 0, right? Because the only time the square of something is 0 is when the thing is 0. So if you don't want that to be 0, you don't want that to be 0, right? And when can this happen? When x is not 3. Makes sense? So put things together now. S of x exists if and only if the input in S, is not 3, right? So thus the domain of S, thus the domain of the function S is, if you want to write it in interval notation, it means all real numbers except 3. So you're going to go minus infinity to 3, skip that 3, and take the union with all the elements that are bigger than 3. And if you want to write it in set theoretic notation, we adopted this in class as well, right? So all real numbers throwing away the set consisting of just the element 3, right? So this means it's a set theoretic minus. This is a minus between a set and another. We're throwing away this guy, this set, from this big set. We're throwing away the set consisting of just the singleton 3 from the set of all real numbers. We get exactly this. Okay. All right. So this is the end of this section.